So I'm Manya, and today I'll be presenting on Mosaic. Mosaic is a compiler for Tensor Algebra that lets its users interact with other Tensor Algebra systems within it. But before I precisely define what Mosaic is, I want to talk a little bit more about the state of Tensor Algebra systems today. So there's been this explosion in the number of high-performance systems. There are libraries that we know, like BLAS and Intel MKL, that have been around. There are newer approaches to sparse tensor algebra, like the Taco compiler and the Stardust compiler. And at their extreme, you can even think about the Intel AVX vector processing unit as really just being a system for tensor algebra computation. Namely, it computes vector element-wise addition and multiplication for vectors of a certain size. And the implication of having such a huge variety of high-performance systems is that these systems often have different specializations. Some systems, like I mentioned previously, are libraries, meanwhile others are compilers. And the key difference here is that these libraries often tend to hand-implement optimizations for some hand-picked number of expressions. And so they tend to be really fast for that restricted set of expressions. Meanwhile, compilers can tackle tensor algebra in their complete generality. Some systems can operate on sparse data, so they can compute on compressed data structures. Meanwhile, others cannot. Others might even choose to optimize for particular types of mathematical structures or different types of data properties, like whether the tensor is symmetric or Hermitian. And finally, they can even target different platforms. So OpenBLAS targets the CPU, QSparse the GPU, and Stardust Capstan, which is reconfigurable data flow architecture. And to get really good performance for the application that you want to compute, you want to be able to exploit these system specializations to get good performance. You want to choose the system to do what it's best at. So let's try doing that for the case of STDMM, sampled dense matrix multiplication. Here, we're going to sample the dense multiplication of C and D using the sparse matrix B. So the first way you could go about computing this using one of these systems is pick a compiler like Taco or Stardust. These compilers tend to fuse code by default, so they will automatically only compute the correct dot product of the rows and columns of C and D that eventually get used in the output. The next way to do this would be to instead target the dense multiplication of C and D using Intel MKL or OpenBLAS. Here, one thing to note is that you're implicitly unfusing the computation. You will compute the whole C and D product, even though some of that result gets thrown away when you sample with the sparse matrix B, and you still have to handwrite the sampled matrix multiplication by hand. Similarly, instead of using a dense matrix interface, matrix multiply interface, you could have used a dot interface. And finally, you could have instead used an interface for performing sparse sampled element-wise matrix multiplication. Again, hand implementing the dense matrix multiply. And these different ways of computing the same thing have real implications for performance. So here we're going to look at how the performance for the STDM expression will change as the sparsity of B will rise, so the density of B will rise. So let's look at the first way, which we talked about previously, Taco, where we're going to compute the full expression using a fused implementation. As expected, we see Taco's runtime steadily rise as the density of B increases, because the work that Taco does corresponds precisely to the number of non-zeros in B. On the other hand, if we look at an implementation where we compute the CD dense multiplication using a CBLAS interface, choosing to hand implement the rest of the expression, we see a flat line. This is because of the unfusing, because we always will compute the whole CD dense product no matter what the sparsity of B is. And this really interesting trend happens here. There's a crossover point. In certain cases, at the extreme, we can see CBLAS implementation beating out the Taco implementation by almost 2 orders of magnitude. And this is because even though it's doing redundant work, which is computing result that will eventually be thrown away, it's still pretty fast. But this is not really the complete story. At the top here, we have a line which represents what the performance would be if we used an MKL dot to compute the CD dense multiplication. And the reason why it's so high is because we need to spend some time rearranging data in memory so that it matches with the constraints and the expectations of the MKL dot interface. So it's not simply sufficient to just piece highly performant pieces together. There's maybe some cost with data overhead associated that we need to deal with. But really the key here is that there's no globally optimal choice. It's hard to just directly pick the best implementation for the application you have at hand. And here I only chose to vary the sparsity of B. There are several other things, like the mathematical structure of B, that one could choose to vary. So we would want an approach that is able to combine both fusion and hand-optimized library calls to get really good performance. But we saw previously some of these systems simply can't compute an expression that users might want to compute. So we still want to preserve the generality of a compiler approach. We still want to be able to target all of tensor algebra. And this leads me to Mosaic. So the Mosaic compiler is a compiler which can be extended with external systems. So you can extend it with MKL, QSparse, perhaps some system that comes up in the future. And what Mosaic does is it'll compose these systems together to compute what the user wants to compute, filling in any gaps that these systems can't fill, and also gluing the interfaces of these systems together. So it will rewire the input-output tensors and compute anything that can't be computed from within an interface from the systems. And to see how we go about achieving this, I want to talk a little bit more about the design of the Mosaic compiler. So we start off with Taco, which is the compiler we've been talking about, and we're built on top of Taco. A user will write the expression they want to compute in Taco's IR, so that's prior work. Mosaic will take in a list of external function interfaces, which indicate what interfaces from what external systems are available for it to use. There's a scheduling language that helps decide function placement. So it will place functions substitute functions in terms of expressions, and it can bind these functions to these sub-expressions. Mosaic will then in turn validate these bindings against the external function interface that was previously plugged in. And optionally, we also provide an automatic search. And this is really just an enumeration of the feasible way of substituting a sub-expression with an external function interface for a given expression that the user wants to compute. This doesn't choose the best performing mapping, but it'll list out all the possible spaces that one can choose to look at. And the key here is that there's this separation of responsibilities. An applications engineer can write the expression they want to compute. An external library engineer will write the external function interfaces because they're experts in these systems. And a performance engineer can describe function placement. And these three people can work independently of each other. So let's start at the obvious place. So how do we go about extending Taco with this external function interface? To do so, we must answer two questions. First, we must be able to answer the question of what the function computes, so what expression it targets. And if we know what it computes, how do we actually generate code targeting it? In this talk, I'll mostly be focusing on the question of what the function computes. So let's look at the scope of the current functions. So there are libraries like MKL and BLAS, which target dense linear algebra for a fixed number of expressions. So you can really think about these libraries as picking out points in the space of sparse tensor algebra expressions. Meanwhile, there are other external systems like tbliss that can perform dense tensor contractions and additions. So they can really carve out this infinite subset within the space of tensor algebra expressions. And finally, there are compilers like Stardust that can compute all of tensor algebra. So there's this huge variety even in the scope of all of these functions. And to capture this huge scope, we use three components. The first component is the most general component. It's a checker function, which is just written in C++. So it's just a C++ function that will return true or false if passed in a statement in our IR. And because it's C++ code, it's the most general you can get. The problem here, of course, is the fact that this function is opaque to Mosaic. So while it's trying to determine feasible schedules or trying to transform expressions to fit within the constraints of functions, it can't do anything intelligently. It has to ask this checker function constantly. So as to expose more information to Mosaic, we add two more things. So the first thing we add is this notion of tensor properties, which at a high level tries to answer the question of what the function accepts. So what kind of data it's willing to operate on. That is, what kind of format is there, symmetric, whether the tensor is symmetric or Hermitian. And finally, we have a language-based approach to try and answer what expressions can the function target. And I want to expand a little bit more about this language. So let's look at tbliss tensor add, which is the function that will compute the addition of two tensors. The key here is that this function can not only operate on tensors of order 1, it can also operate on tensors of order 2, order 3, and so on. So this is capturing an infinite subset of tensor algebra in general. And it's impossible to simply enumerate these expressions one by one using Einsum notation that has been used in previous work. So in order to capture this infiniteness of this expression, we introduced the notion of a dynamically sized index variable list. So you can instead index into a tensor without fixing the order of that tensor. And in addition to making this addition to the prior work existing language of tensor algebra, we also add this notion of being able to add constraints on an infinite, a dynamically sized index variable list. This is because even though your index variable list might be dynamically sized and the expressions you want to compute might still be infinite, you still want to maybe impose some constraints on them. So a for all or there exists condition will impose a constraint on all of the indices in this dynamically sized list or on only one of these indices in a dynamically sized list. And eventually, when we end up doing our validation, we use a parser to make sure that the operator pattern matches, and we lower the condition to the Z3 solver to make sure that we satisfy any conditions on these indices. So that was the external library interface, and that's how we end up adding new functions. But now that we have functions, how do we end up actually targeting it? So now I'm going to talk a little bit more about the scheduling language. And for the purposes of this discussion, I'll mostly be focusing on using Intel AVX intrinsics to compute the STDMM expression that we've been looking at. Even though sometimes it's not the most performant, it's still an interesting expository example that will be useful to talk about the capabilities of Mosaic. So the first, most easy way one can go about scheduling STDMM to Intel AVX intrinsics is to first write the statement of STDMM, register AVX dot, which is the external function interface to Mosaic, ask Mosaic to produce all schedules, and pick one of those schedules in some way. So you can add an auto-tuning step in the middle, but right now I'm just picking one randomly. But let's look at actually one of the schedules that Mosaic might end up producing to see what the automatic search really looks like here. So this is a schedule that's going to be generated by Mosaic when you ask Mosaic to generate the schedules for STDMM using AVX. So the first step that we need to go through is we need to match on operator pattern. Here, crucially, Mosaic will reject all information about tensor order and tensor dimension size. And this is what really makes our search fast, this ability to reject extraneous information at this step. And once we find a match on operator pattern, we're going to isolate that expression from the rest of the expression we want to compute. So that's the pre-compute step in this case. Next, we're going to try and determine how to actually now resolve constraints on tensor order. We notice that the compute capability description of AVX can only operate on vectors. So we're going to need to fix certain indices in the STDMM expression in order to actually be able to target the Intel AVX intrinsic. The next constraint we must satisfy is the fact that the length of the vector must be equal to 4. So in this case, Mosaic will generate a Z3 solver query, split the appropriate index, and reorder the splitted index so that we actually end up computing the same thing, the correct thing. And finally, with all of these transformations, we'll call the bind scheduling command, which is actually the command that performs this function substitution. So this will indicate to Mosaic that we want to perform this substitution right now. And while this is a schedule generated by Mosaic, you can also write it as a performance engineer if you want to have precise control over tiling factors, or you just want to explore a bunch of things on your own. And to demonstrate how general our approach is, we end up plugging about 11 expressions across 7 systems. So these are the systems I've been talking about, including compilers like Stardust, which are for specialized hardware. And in total, we end up adding about 38 external functions to Mosaic across all of these 7 systems. And it's not really very hard to add a new system. It only takes about 20 lines of code on average. And Mosaic can access the different performance regimes we've been talking about till now. So Mosaic could access sort of the different crossover points in the SDMM expression I've been talking about. I've just added performance numbers for all of the systems that we added and we scheduled through Mosaic for this SDMM expression. So there's a wide variety of things you can choose from. And that's really what Mosaic is. So Mosaic enables its users to pick a single host compiler as opposed to picking one of these systems to write their expressions in. So they can evolve as research continues to evolve and pick the best system where it's good at.
Great, so we have time for questions. And again, if you have a question, please come up to the mic so that we can hear both in the room and online. So maybe I'll ask a sort of high-level question to start. What's the next step for Mosaic following from this paper?
Oh, that's a very good question. I think so the obvious research direction is to build the auto-tuner, so pick the best schedule out of all the options that we have produced. I think that would be the next obvious step in terms of research.
Great, and please say your name and affiliation if you don't mind.
Hi, my name is Rafe. I'm from University of Illinois. Great talk, Manya. I had a question. So how does the compiler reason about different layout requirements for these different libraries? Does the user have to provide the layout transformations if you want to interoperate between different libraries?
Oh, right. So you mean the data structures
Yes.
for external libraries. So I didn't really go into this in this presentation. So basically, we have this notion of setup, the actual function that computes the expression you want to compute, and tear down. So setup can take in a list of other external functions that can transform between different data structures. The user needs to write this transformation. Mosaic can't automatically reason about how a Taco tensor will translate to a BLAST tensor. But you only need to, if you do it right, you only need to write that once.
So, and you do it from like a common representation, or you have to do like a cross product of all different layout transformations?
Oh, so right now the approach is cross product, but it depends on the user how they choose to do it.
Okay.
Yeah.
I see. Thank you.
Yeah, it's really easy for users to not do the cross product representation.
Thanks.
Hi, I'm Saul. Thanks for the wonderful talk. I was curious at a high level how this compares to systems like TVM. Are these different levels, or would one use the other, or how would you talk about them together?
Yes, so I don't want to say something that I'm not entirely certain about, so maybe take this with a grain of salt. But from my understanding, or stuff that I've just looked at, TVM tends to focus on intrinsics or just instructions, as opposed to we can make these high-level substitutions, and we can do it for sparse formats. So I think that's sort of the key difference.
Thank you.
All right, well, let's thank Manya again for a great talk.